Hello, my name is Joshua Evenson. I'm an engineer here at Meta. I've been here about 8 years. I work on the Messenger client, iOS, Android, desktop, the Apple Watch. There are many. I spoke at F8 a few years ago about a project that we did here at Meta called Lightspeed, which was a rewrite of Messenger iOS for high performance. As part of that, we rewrote all of the Messenger features onto the new stack. So I know a little bit about scaling product development. There are a lot of challenges in Lightspeed. I want to focus on the tension between scaling the number of features and the number of developers on an app and maintaining its performance while you do that. I don't have time to talk about all of the challenges, and there are many, but I'll talk about a few that I think are the largest scaling challenges. So what makes product development hard on large systems? Complexity. I like to describe it in terms of concept count. How many concepts does a person need to understand to do their job at a certain layer? The best way to manage complexity for a developer is to add a layer of abstraction to abstract it away. But this is an issue for performance engineers, as understanding how the system works is one of the better avenues to optimize it. Adding an abstraction layer adds extra complexity. So each layer adds the total number of concepts the performance engineer needs to know to do their job. So this is the first and one of the primary scaling challenges if you are scaling to a very large org. Do you maintain a small set of abstractions and concepts to make the system easy to optimize? Or do you build a lot of clean abstractions to make it easier to scale development? It's a tough challenge. How did we approach it? We started with patterns over abstractions. People usually just want to copy code. This is why Stack Overflow is popular. Making code that's easy to copy correctly tends to be better than adding abstractions right away. Another way we approach this is having one way to do things for 90% of the cases. People will want different libraries for different things. People might ask for 10 different networking libraries. That adds a lot of complexity for performance engineering. The better approach is to have one networking library, even when non-optimal, that's used for all use cases, except for a couple of exceptional cases. And people won't like this one way of doing things. And so it's important to focus your org on global optimizations. You have to look at global metrics. And when a team has a local metric, a metric for their team that is different from the global metrics, you need to make sure that that team is thinking of both and setting trade-offs appropriately. And finally, when you need an abstraction, it's better to use common concepts. Using an existing library, of course, or when building a new library, using existing systems. Reducing the total extra common concepts, even when a layer of indirection is necessary, reduces the total concepts for the system. And it's extra beneficial when the concepts are transferable across the company, or better yet, across the industry, because it makes them attractive to learn. Learning a very popular language tends to be more attractive to developers than learning a language that's specific to a team. So to explore other scaling issues we had, let's pretend for a moment like we're building the new version of Messenger. And let's talk about app start. The start of an app, the cold start time, the time it takes to start the app up and show the first screen, is critical for messaging. Messaging is not generally a consumptive app. It's not the kind of app that you generally go to watch 30 minutes of TV. It's a utility app. You get a message from someone, and it's very important you read it right away sometimes. And so it needs to start immediately. It's easy to start fast. When the app first starts up, you load the inbox and it works. But as you add more engineers, more features, you start to add a little more. It's better to resist immediately adding new systems to manage this until you have a problem. Often, you can just let things be slightly slower, and as long as it doesn't affect the metrics negatively enough, it's better to have slightly worse metrics and less concepts in the system. But eventually there are too many features to load, or there's too much to do. And you kind of end up with two problems. One is that you're at a perfect critical time and there's too many systems trying to do too much work. And even the loading of the code necessary to do the work could be too much. So this is our next scaling issue, which is code volume. At a very large company, there's a lot of engineers writing code. On a backend system, this doesn't matter as much. But on a mobile client where performance is very, very constrained, it becomes a problem. Primarily, it's a problem because of too many systems trying to do work at perfect critical times. It's an orchestration problem. But, like I said, loading code can be itself a problem. Disk I/O is one of the slowest parts of very old mobile apps or very constrained mobile apps. Usually the CPU is actually not so bad, but getting things off disk is very slow. And so having too much code that has to load right at app start can be a performance blocker on its own. How did we deal with this? Well, nothing completely new. We added a plugin system. This allows us to categorize features by core features versus non-core features, where a core feature is something that needs to load when the app loads. And then once we've isolated those, we can move the non-core code into a separate dilib on iOS or shared object file on Android to reduce the total volume of code we need to load when the app loads. After this change, we could scale our features pretty well without affecting app performance. But this shows another problem. We have a lot of data moving around the app, and when you split components up, there's a lot of data moving between this plugin abstraction. And this can get very complicated, in particular because while there may be only n plugins, because many plugins can depend on other plugins, you can end up with some combinatoric interactions between the data of different pieces of the app. This shows itself best when dealing with updating the UI. Different UI elements can depend on different parts of the system, and reflowing them all properly can get difficult when you have enough systems and enough engineers writing code in those systems. And this is our third scaling problem, data complexity. As you scale up the features in your app, you scale up the data dependencies. So we need a framework for managing this, and it needs to avoid adding too many concepts to the system. This is not a problem that's unique to us. There are many types of frameworks that solve this exact problem already. A good example in the React space is Redux. It's a library that's meant to solve the problem of having a lot of data interrelationships and making sure that they're managed well and that the UI updates properly. In our case, we built our own framework instead of using an existing one. And there's a couple reasons for that. First, the performance of existing frameworks that we looked at wasn't good enough for our purposes. We had very, very tight performance constraints, and we needed the system to have both itself very good performance and a lot of controls over the performance of the code that people write. Also, we targeted a very small binary size. The whole system had to be less than a few hundred kilobytes. So no framework that we looked at could match this. And we wanted a system that could linearly scale its total features without also linearly scaling the concepts we have to add to the system. And so we needed a framework that was very expansive and broad. So what did we do? We made the app database-centric. Namely, we based the whole app around SQLite. Why SQLite? Well, namely, it gives us a SQL query language, which is a very expressive language for managing data. And so it contains already most of the concepts that we need to be able to scale up the number of features we add. And SQLite gave us a lot of control over performance and a lot of information about understanding performance. What does it mean to be database-centric for the actual app? It means a lot, but two important things. First, app logic lives in the database as stored procedures. So I'll get more to that in a second. Second, the UI layer is a thin layer that just reflects the state of the database. What are the benefits of this? Well, first, there's a single source of data across the app, since almost all data lives in the database. Instead of having to have different components interact with each other, everyone gets to interact with the database, and they can affect each other by affecting the data in the database. Second, our business logic lives in a database, and the database is transactional, so our business logic gets nice ACID properties. Sometimes as you scale a system, having many different components editing data, you can produce intermediate states or partial failures, and we don't have to worry about any of those because we have transactions. And finally, SQLite has a very low binary size since it's already present on most apps, and it has a lot of tools to manage specifically disk I/O. The queries in SQLite give a lot of control over which tables are pulled, which tables are joined, how much of each table. And so we get to manage our most constrained resource. So let's talk about implementation. How did we actually build this system? Well, at the UI layer, as I said, the database contains all the state for the app. When we want to render a view, the view executes a query, and that query is its view model. And so the UI layer gets to stay very thin, the business logic gets to stay in the data layer. For views that are part of the core, often, external plugins need to edit the way they look. Those core views are written as templates. Developers can choose and affect how the core UI gets rendered by adding data, removing data, or setting some columns as null. And so we can scale up the number of features we have and the ways that they interact with core without having to scale up the amount of code in core. So we render the UI pretty simply. It's just based off of the database. How do we write the business logic that decides how the database changes? We built our own language for this called CG-SQL. It is open source now, and the link's there if anybody wants to use it. What does it look like? Well, we can define our schema here. It's a normal SQL schema, but with some extra pieces. First, it manages versioning for you. So when the app updates, it will handle things like dropping data, mutating data, changing data between old and new schema. This is really important in mobile apps because you want the upgrade experience to be very clean. It also provides regions to schemas, let you manage data access. You don't really want to just declare everything as a global. You want to make sure that certain components have access to certain data, and this lets you do that in a very clean way. So when it comes to actually writing these queries, CG-SQL lets you intermix normal imperative programming with SQL. View models often need more than just a query. They need some complex logic, maybe for some user information, for merging data, for validating data. You can put all this kind of logic in the same procedure and then run your query, and it all gets run together. One of the problems that SQL often has is that it is not very scalable because it does not allow a lot of code sharing. This is compacted in SQLite because SQLite doesn't have anything like parameterized views. If you write a query, that can have parameters to it, but if you have a view or if you have something you want to reuse, it can't. CG-SQL adds this. It adds fragments, which allow you to build composable pieces that you can use to build up queries and allows you to really scale the system well. And finally, it generates its code into C code that interacts with SQLite. So it works across all of our platforms. So it's nice. You get to write the logic once, and it works across all the platforms. So now we have a UI that's based off of queries. We have a data layer with logic to allow us to manage reads and writes. After these reads and writes, how do we actually reflow the UI? Well, we register a number of hooks in SQLite. SQLite provides an update hook and a pre-update hook that tell us which tables and columns have changed in the database, and a commit hook to tell us when the data is committed and ready to read. So at build time, we take the set of queries, we map them both to the UI elements that depend on them and to the tables that are used in the queries. When data changes in any of these tables, we rerun the query and vend that up to the UI elements that need to reflow. So it's a very safe and stable system, very difficult to miss reflowing data that's changed. What about data that's external to SQLite, like data that comes out of operating system level systems? Fortunately, SQLite has virtual tables. These are tables that talk to C functions instead of disk. And we can use these to expose data that isn't in the database, but that's needed for some UI queries. And there are a huge number of elements inside of SQLite for managing performance. So without having to change the queries or change the way the system works, we can do a lot of optimization work. Some of the things we use are things like wall mode, which makes SQLite write to an append-only file and reduces a lot of flashware. SQLite profile provides an excellent amount of profiling information, so we're able to look into SQLite and understand where the performance bottlenecks are. It has a query plan explainer that we use. We parse that, and we help and we output suggestions for queries to help people realize when they need an index or when they're doing a table scan that's unnecessary. SQLite has a progress handler that allows you to cut off long-running queries so they don't cause system stalls. And it has a lot of pieces for managing when data is written and pulled from disk. Like the synchronous pragma lets you manage how often data is flushed to disk from memory. And there's obviously a lot more, but these are some of the examples of things that we can do without having to add a lot of more concepts to the system to manage performance. So obviously, there's way more scaling problems. And I only had time for these three. But I think these are three of the big ones when you scale up to many features and many engineers. So for concept management, at the end of the day, we're careful about how we add concepts to our system. We only do it when we are sure we have a significant scaling problem. We try to follow the whole build, measure, optimize idea. And even when we do add indirection, we try to solve many issues under a single umbrella. So we don't have to add many different abstractions. For code volume, we split up our code into core and non-core. And we try to minimize the amount of code we load and the number of systems we run during critical times. And for data complexity, we built a database-centric design around SQLite so that we have a scalable mechanism for providing data to the whole app, for providing all the features that each feature developer needs, and still providing a lot of optimization capabilities. So we learned a lot from building Lightspeed, and I hope you learned some of what we learned in this talk, and hopefully it's helpful for you in scaling your application. Thank you for your time.